Welcome to my second Python data analysis video. After my previous video, I got some comments that people wanted me to do some visualizations and some charts. So that's what I'm going to do today. So today we'll be working with a chess dataset. Once again, if you want to find the original dataset, you can find it in Kaggle. I will drop the link. In Kaggle, I found this chess game dataset from Lychess program dataset, which covers 20,000 plus Lychess games. It includes the game ID, rates, start, end times, who is the winner by color, and their ratings, and so on. And I thought about covering these three topics. First is data cleaning and preparation. We'll see what's the data we're dealing with, and what can we do to improve it. Then we're going to analyze the rating brackets. We'll see the average amount of turns per bracket. We'll see what openings are popular in each bracket and what are the most common outcomes. And finally, we'll analyze the openings themselves. So, what openings have most black victors, white victors, what openings have the biggest draw rates, and so on and so forth. So, without further ado, let's begin. And the first thing we need to do is to download the data. Just like before in Kaggle, you simply click download and you save it in the same directory as your Python file. So since I've already downloaded that, I can simply open the file. Let's see if it works. It seems like it does. We have a data set with our IDs, rates, so on and so forth. 20,000 rows. That's a lot of information. Hopefully we'll get some insights from this. Also, one thing I forgot to mention is that I've already imported all of my libraries that I'm going to use. And also, if you're confused about this cell right here, I've simply identified the color palette that I want to use for my visualizations. So these are the custom colors. If you want, you can copy them from the link that I will provide. But what this cell does is pretty much sets the palette colors and the default sizes for all of my charts. So, okay, first let me zoom in a little bit so that we can see what we are working with. Now, first I want to see the information about our cells, about our columns, and what nulls do we have. We can see that none of our columns have any nulls, so there's no missing values. That's good. All of our columns have 20,058 rows. First thing we will work with is the average rating of a match. So we only have the white rating and the black rating. Naturally, the very first thing we need to do is to create a new column named average rating, which will just have the average of those two ratings. So let's do that. Now let's see if it works. It seems that it works just fine. So we have the white rating, the black rating, and we will assume that the average rating of the match is this. I'm not sure how correct this is, but this is how I want to do it, so that's how I will do it. So sorry if there's any chess geeks that don't agree with me. All right, next. Let's see what is the range of our ratings. So the smallest average rating is 816. The biggest one is 2475. So the next thing I want to do is to split all of these individual ratings into rating brackets. So everything that's between 800 and 900 will go into one bracket, then another one, then another one. I will increase them by increments of 100. So let's define our function. So what our function does, it creates a new column named rating brackets. It takes the value of average rating and applies a custom function called brackets. So now let's define our brackets function. After I'm done writing it, I'll explain what it does and how it works. Let's first see if it works, and if it does, then I will explain. Value counts. So what our function did, it created these brackets. So we have 10 cases of average ratings in this bracket. Then we have 83 in this bracket, and so on and so forth. We will visualize them, and we will see how it actually is distributed. Probably it will be a bell shape. But now let's return to the function and see how it really works. So we take the value of x here, which goes to brackets x, and we see, since we know that the lowest value is 816, we started by defining our n by 900. So while our number is smaller than 2600, we take our x, which, for example, if it's 816, and compare if it's smaller than n. If it is smaller than n, then we return an f string, which says that our n, which is 900 minus 100, so it's from 800 until 900. If not, then we increase our n by 100, and we just do it for all of our values until we've reached all of our points. Hope that makes sense. I know that this while loop isn't the most efficient way of utilizing our memory, but hey, if it works, it works. At least I've saved some line space here. So yeah, what can we do next with this information? So one thing we can do is we can clean up our data a little bit. Since we have these four brackets that are they have below 100 cases, we can decrease the noise by combining them into single brackets. Good thing for us is that they're all consecutive. So we've got 800, 900, 900,000, and then we have from 2300 to 2500. So what I will do, I will combine these two into 1000 minus, and these two into 2300 plus. So let me do just that. Okay, let's see if it actually works. And it does. Good. So now we have our separate bracket for anything below 1000 and anything above 2300. So how it works is, first we take the column rating bracket and we replace any value that's 800, 900 with 900, 1000. So we just bunch it up into one place. And then we do the same thing. We take all of what is 900, 1000, and we replace it by 1000 minus, and we do the exact same thing with this, just without except for the minus we take the plus sign. So we have these two brackets. Both of them are still below 100, but at least they are somewhat representative of the smallest and the biggest brackets in our dataset. So let's continue by actually visualizing what we have here by creating a bar plot. So once again, I will create a Seaborn bar plot. Since Seaborn, I'll just remind you, is a library that we've imported right here. It is extremely visually appealing visualizations. So you'll see what I mean. First, let me create a basic bar plot. So what we have here is, just as expected, a bell curve. And we can see that the most popular, the most occurring rating brackets are from 1500 to 1600. And I just did a quick Google search, and I really found that the median rating in Lychess.com is 1500. So it means that our information should be somewhat reliable. What we can also do is make this more visually appealing, because right now it is decent at best. So we can insert some additional parameters, such as palette, and custom color is something that we defined at the very beginning. If we go to the beginning, we can see that our custom color just as I mentioned before, is this palette of colors that I've customly adjusted by myself. So if we enter this palette, we'll see that our colors are shades from yellow to black, which is better, but still not the best. We can add some additional parameters such as edge color, which adds this little edge at each of our bars. And we can also increase the line width of our edge color. Now this looks much better. Also, let's annotate pretty much everything. The x-axis, the y-axis, and everything in between. So we've got our title. Also, let's add the labels of axis. We've got our axis labels. And finally, let's add the x and y ticks. All right, so this looks very nice, at least subjectively to me. The X ticks and Y ticks, as you see, it just emboldens the X and Y tick marks, and we've rotated the X ticks 45 degrees in this with this rotation parameter. So just to run down once again, we've created an SNS bar plot. X is defined as our index of our value counts. As we can see, we've already used these value counts, so we're reusing this as both for X axis and for Y axis. Just for X, we're looking for the index names, which are these bracket names, and for Y, we're looking for the actual values. If we didn't have this order sort, then they would be in this order that you can see right here, which will be just scattered around randomly. So we've specified the order. We sorted it by DF rating bracket. And that's pretty much it. Yes, we've specified the palette, which we've defined at the very beginning, edge color, line width of our lines, and we've defined all the titles and labels. So that's how visualizations in Python work. So this answers our very first question. Let me just remind what the question was. We'll make a markup cell and we'll just copy what we have over here. Average amount of turns, which is actually not what we did here. We just analyzed the actual brackets. We will do the average amount of turns right now. So to do the average amount of turns, we already have the skeleton of our visualization. We'll also use the bar plot. It will be a little different, but everything in due time. So first thing we'll have to do is we'll have to group by our data frame by our rating brackets that we've created successfully. And we're looking for amount of turns, mean. So it's the average amount of turns per each rating bracket. So this is the information that we have. And now that we have this line right here, we can reuse the whole code that we already had. And the only thing we'll have to change is the X and Y axis. So we can just copy the group by rating bracket here. We'll once again use the index for x-axis and we'll use the values for y-axis. Also, the order is actually we don't need, or do we need? No, we also need the same order. Let's see if it works. Okay, so the average amount of turns looks like it's increasing by a little bit, but at pretty much a constant rate. But I want to see the exact values above each bar plot. And to do that, we'll need to add some additional functionality to our uh, formula right here. So let me just do it. Okay, so a lot to digest here. This is something that I will be honest with you guys. I googled myself how to do these annotations, but basically, for what it does is this for loop searches for each bar in this formula right here, which is plots that patches. Plots for us is our SNS bar plot, and for each bar we annotate it, and the format here is like this. This right here defines this two decimal points format. uh, we get the bar height, then we first define the x location, x position and y position of our annotation point. So we get the bars x point, then we get the bar's width and divided by 2 to get the actual center point of each bar. Then we get the bar height, so it's right here. And HA and VA means horizontal alignment and vertical alignment. Both are aligned centrally. Size of the font, the text, where the coordinates, where it begins, where it ends, and text coordinates of set points. I'm not actually sure what this means, but I saw this in Google, so I'll leave it like this. So I'm going to be honest with you guys. Sometimes I also need to Google some things. But yeah, this is how the end product looks like. And I'm pretty happy with this. So now we can actually insert the name of our task that we've just completed. Average amount of turns per each bracket. So what we can see here, that there's a gradual increase in average turns count as we move up the rating bracket, well, with some exceptions right here and maybe right here. I think that this can be explained by some additional insights, such as the more experienced the two players are, the bigger the likelihood for a game to reach the end game stage. So that's my deduction. And also, maybe experienced players are less likely to be caught off guard by an unseen opening, knowing exactly how to react. And maybe we can also say that the smaller the rating of two players, the higher the likelihood of blunders occurring, meaning that a player might lose a winning game in just one or two turns. So that's the insights that I can provide from this visualization that we can see here. All right, moving on to the next question, which is openings by ratings. So before we can actually dig into our openings, let's just see how many different openings we have. So we have almost 1500 different openings. Well, I'm not a chess master by any means, but this seems really off. So let's take a look at these openings. Maybe there's something we can clean up in this situation here. Okay, so I've printed all of the 1500 openings, and it seems that there is quite a lot of data cleaning we have to do because there's a lot of variations. You see something, something variation, something, something variation, and there's some semicolons. Uh, just for the sake of simplicity, I will clean this up in a way that I feel that makes sense. And after I'm done, we'll discuss if it makes sense. All right, let's see what openings we're left with. Well, there's way less, but there's still quite a lot. So let's discuss what I've done up to this point. I've applied a lot of Lambda functions, and I've split all the text of opening names. So I've split everything that has a semicolon to have only the first half. For example, let's see an example with a semicolon. Russian game, semicolon, French attack. So a Russian game is a Russian game. I don't care what's after the semicolon. Then we have these symbols, not sure how they're called, right here. So if it's a Philidor defense, then it's a Philidor defense. There is no variation. There's no lion's claw. Then we have these hashtags. Not sure where they are, but I saw some hashtags. Oh, for example, number two, English defense number two. No, that's just English defense in my book. And then there's a bunch of accepted, declined, and refused. So I also don't care about those. Once again, sorry to all the chess geeks. If these are important to you, you can just ignore this part and you'll have a lot more openings. But I'm not sure how to analyze 1500 different openings. Okay, so we're left with still quite a lot of openings, and let's think if there's anything else we can do to make this a little bit more concentrated. Okay, so I found quite a few, to my view, duplicates. So we have king spawn game, we have king spawn opening, and then we have king spawn. I'm not sure if they are different, so I've turned them all into king spawn. Then we have old Indian and old Indian defense. I'm not sure if there's a difference between those two. And also there's queen spawn game, queen spawn, and queen spawn opening. They will all be turned into queen spawn. Also, we're defense and we're opening. So, after all of this cleaning, let's see the length of our opening set. Okay, so we're left with 122 openings, which sounds way more realistic. However, most of them were played less than 100 times, meaning that any findings that we have with them might have some bias. Let's create a second data frame to analyze only those openings which have 100 or more occurrences, so that the insights that we find, we're sure that they're more or less without bias or without any outliers. It seems like it does. The smallest dataset is Mises opening with just 103, and we're left with, let's see, the length. We're left with 39 openings, which comprises about 90% of our whole data set. So that should be reliable. Why I say 90%? Because in the beginning we had 20,000 rows. Right now we have 17,000 rows, so that's pretty much around 90%. Now that we're done with cleaning up our data set, we can move on working with the opening names. So to visualize how the frequencies of our openings are distributed across our ratings, we will need to create a heat map. I've done this in my previous Python video, but last time I've created a pivot function, and this time I will show you how to do the same thing without the pivot function. So first thing, let's group by our data frame. So if we group by our rating bracket and our opening name and we take the size, we can see this group by object and it displays each rating bracket, its opening name, and how many occurrences we had with these combinations. It's not very informative, so what we can do to turn this into an actual table is we can use the unstack function right here. And now we have this unstacked data frame right here. But we also have a lot of NaN values, so we can just use the fill Na function, fill it with zeros. Now our NaNs are filled with zeros. We have no missing values, but one thing we also have to do is we'll have to convert these floating points with decimal points into int. So we use the as type int. So just like that, we have our very own custom pivot table of our rating brackets, opening names, and the number of occurrences that they had. Now, once again, I will create an SNS heat map. And once I'm done, I'll show you how it works. So I've prepared the formula in advance because it's quite a lengthy one. I'll see if it works, and if it does, then I will explain to you guys how it works. All right, so we have our heat map. I'll just zoom it in a little bit so we can see what's going on here. So first, how the heat map works. So the brighter the color, the bigger the value, the bigger the proportionate distribution of openings in that particular bracket. Meaning that each bracket's row, for example, 1000 right here or 2300 here, the sum of all of these values will be 100% or 1. So the heat map only works for each row, not for the whole data set, but for each row. Now, with this information in mind, we can see that there's two very distinct color patterns here. So, for example, King's Pawn, the higher we go, the more popular it gets. So this means that it's very popular with the lower brackets, and the higher the bracket goes, the rating bracket goes, the less popular this opening gets. The exact opposite can be said about the Sicilian defense right here. It's unpopular with the lower brackets, and the higher it goes, the more popular it gets. I'm not a chess expert once more, so if there's anybody in my comments that are proficient in chess, please let me know if this makes sense to you. There's no other insights that could be made. Maybe that this French defense is popular all around all of the rating brackets, and maybe that Queen's Pawn is also very popular as well. Now, coming back to the function and how it works, so there's two parts to it. First is that we've defined this custom figure size because uh, if we would be left with the one that we had before, it would be very small. We wouldn't be able to read anything. And also, this Seaborn's heat map requires once again the parameter of where we get our information. So the pivot table. So in our case, Z right here is our pivot table, and we take this Z. But if we only took Z without applying our custom lambda function, it would calculate these proportions for all of the numbers. So meaning that uh, more vacant rating brackets, for example, 1000, would have all of these zeros because there's just very few openings here. So we've applied this custom lambda function so that this mapping in this heat map is applied for each row individually, meaning that each row, if we sum up their values, it has a sum of 1 or 100%. So that would eliminate some noise and we could see the tendencies in these brackets. Otherwise, we couldn't make any deductions since if we go back to our bell shape here, there's a huge difference between, for example, 1000 rating and 1500, 1600 rated players. There's just way more instances of this bracket and this bracket. So that eliminates the bias. And everything else is pretty usual. We annotate the X-tick labels, Y-tick labels. We use the custom color map. We annotate each cell. This right here shows the format of annotation. So once more, 2 decimal points. We've eliminated the color bar, which would be like a legend at the very right. And we've annotated all of the X-ticks, Y-ticks, and labels. So yeah, that's how this heat map works. If you want to reuse such format, once again, you can find it in the attached link in my Kaggle worksheet. So we can now say that we've answered the second question. We can insert a cell below, make it a markup cell by clicking the M button. And now we just copy our question, which was opening frequencies. Boom. Right, moving on to the next question. So our next question is outcome frequencies by rating brackets. So as far as I know, there's three outcomes in chess. Either white wins, or the black wins, or it's a draw. So we'll have, once again, our bar plots with 3 bars in each bracket, one for white win, one for black win, one for draw. So for that, we'll need to create a new data frame. All right, so what we have here is a table with our rating brackets and the appearances of each outcome: black victory, white victory, and draw victory. Now, what we did with this formula right here is we've kept the same format of our last data frame. It's just that we've normalized all of these outcomes. So instead of having these raw outcome numbers, we have the proportions of each outcome in each rating bracket. So imagine this as percentages of each outcome in this bracket. So this is the format for such a formula. All right, so now we can move on to our visualization. Once again, I've rewritten the formula. I've copied it here. If it works, we'll discuss it, and then I'll explain how it works. All right, so let's zoom in just a little bit. Okay, so this is interesting. As we move up in our rating brackets, the tendency remains clear. White player has a significant advantage. Right here, and over here. Up until we reach the highest bracket, which is 2300 and higher, here the black is much more likely to win than white. But also have in mind that this bracket right here has the smallest sample size. Thus, the bias here is pretty big, and there's it's just several outliers could make a difference. So we'd need more information for this specific bracket to see if this tendency remains. Also, the draw rate here is also the highest. And overall, I can see that as we move up the rating brackets, the overall tendency for a game to end in a draw also increases, which also probably makes sense. Now, let's talk about how this visualization formula works. So just like we did with our SNS bar plot, we've also created this patches. So this patches part right here only annotates each bar. So it creates the number of the exact value for each bar. So this whole part does that. So the format here is absolutely the same as previously, so I won't go into this into more detail. We've discussed this over, let me see, over here. Same format. So since I'm not sure if SNS has this format for bar plots where we have these stacked bar plots, I've used the default dot plot method, which I just specified the kind, which is a bar plot. Uh, I've defined the alpha, which makes each of them a little bit more transparent. The colors, I've made them custom, so I just copied and pasted from my palette over here the first value, the middle value, and the last value, so that there's a contrast between these values. Figure size, because it's a very horizontal figure, so its x value is twice as big as the y value. The width, the title, the edge color, and then just annotation. So I hope if you had no problem with this visualization here, then there should definitely be no questions with this one. But if there are, you can just uh, copy my code here and play with the parameters and see what does what. But I think we're ready to actually say that we've answered this question. So let me just insert the cell below, make it a markup cell, and copy our question, outcome frequencies, right here. Okay, let's move on to the final part of our analysis. So next we'll compare the opening victors, meaning that we'll compare each opening's black win rate, draw rate, and white win rate. So there's multiple steps that we need for preparation. First, let's group by in a similar way that we've done before. So we have our group by object where we have our opening names, our winners. Uh, this format is absolutely the same that we've had over here. And what we've done before, if we remember, we've used this format just to see the proportionate distribution. So we'll do that. And also we'll do one additional thing. So let me just show you. Let's see if this works as I intended, and it does. We've done the same thing as before. The only thing we've added is the transpose method, which switches the x and y axis. So if you remember, before we had black, draw, and white as the rows. Now we have them as columns. So one more thing that I want to do is I want these opening names. Right now they're alphabetical, as you can see, A, B, C, D, E, but I want them to be in the number of average turns each opening takes. So to do that, just follow along. So what this function does is it group bys, once again, opening names. We search for the means, and the n largest, this automatically sorts from largest to smallest. If we didn't do the n largest, we'd have, once again, the alphabetical order. But if we do the n largest, and we specify the whole set, since there's 39 openings, we have this in our mean amount of turns for each opening. So the King's Indian defense, on average, has 70.7 turns per game. And the smallest one is Mises opening, which only has 50. So there's a 20 turn difference between these two openings. So what we need to do now is just take the index names of these opening names. Now that we have these index names, we can simply copy this order of these index names. And once we go back to our data frame df4, There's a lot of these double and single quotation marks, so we'll have to manually adjust those. If you don't understand what I mean, so for example, take Queen's Gambit. Since the beginning has a single quotation mark here and there is an apostrophe here, it takes this as a text and then it really doesn't understand how to interpret this. So for these cases, I have to manually write down the double quotation marks. So some manual labor required here. Okay. Now let's take a look at our data frame number 4. And as we can see right now, it's not in alphabetical order. It is in our custom order. So once again, what we have here is a pivot table where we have the victor, which is black, draw, or white, and we have the opening name. And this opening name isn't just randomly sorted, it is also already sorted by the descending mean amount of turns per opening. So there's an additional parameter that we can consider here. So all that's left to do is to visualize all of this. As always, I've pre-written the whole code, but this one is pretty simple. Uh, we've just used a new Seaborn plot, which is line plot. We specified the data, which is df4, which is what we have here. We specified the palette of our 3 lines. So once again, I use 3 distinct colors from our palette. And I use the dashes equals false because by default, SNS line plot uses different lines with different dash styles. So one would be dotted, the other would have dashes, and wouldn't look very well. And then I just simply wrote down the title, the legend, and so on. Let's see how it looks. Let me zoom in just a little bit. Okay. So we have on our x-axis the opening names. This is the y-axis is the outcome percentage. The yellow line represents the white win rate. The black line represents the black win rate. The gray line represents the draw rate. So as we can see, in most cases, the whites win more than the blacks, but there's quite a few openings where blacks have an advantage. For example, right here, the Indian game, blacks have a 55% win rate, and with the Van Cruijs opening, the black win rate is something like 62%, which is just mind blowing to me. If we compare the draw rates, there's 2 of them at 10% or above. One of them is semi-slab defense at somewhere 10.5%, and the bird opening. And also keep in mind that these openings, as I said, are sorted in the mean amount of turns from left to right. So there's one other thing we can achieve with Excel visualizations is we can annotate with our custom lines whatever we want. So let me just copy the code and I'll show you. So as you can see, with just a couple of new lines of code, we've drawn these red lines and we're showing any highlight points that we want. For example, the highest win rate for white over here is 65.6%. Highest black win rate here, and we've drawn these red lines, and we've also annotated the highest draw rate. So how did we achieve this? So we've inserted this block of code in between our Seaborn line plot function and our annotations of PLT and PLT show. We've annotated PLT.annotate 3 points. The first one is highest draw rate. So let's analyze this one, and all the other ones will be similar to that one. So we're writing down highest draw rate. Then we specify the x and y coordinates of where our point that we want to annotate is. So x is 1, y is 11. Then we annotate the location of text. So it's a little bit more to the right and a little bit more up. So the point is over here. Let me just show you, zoom in a little bit. Point is over here. The text point is over here, a little bit to up and a little bit to the right, right? Hope that makes sense. Then we align the text to be centrally aligned. And then arrow props is just a custom dictionary functionality that describes how our arrow looks. So we have the point of our text, we have the text, and we have the point where our arrow will show. So this dictionary shows the style of arrow. It could be dashed, it could be dotted, it could be simple in our case. This is the line width. This is how wide our arrow is, and this is the color. And we've done the same thing for all three of these parts. So that's how, if there's, if you're presenting your findings to some shareholders or some colleagues, this is how you can highlight the points of interest with Python. All right, so I think we've answered this question. Once again, insert below, make it a markup, and let's copy our question, which is analyzing openings by opening vectors. This. Okay, and moving on to our final question. So our final question will be analyzing the opening outcomes. But before that, let's see how our victory statuses are displayed or distributed, I mean. So, as we can see, roughly half of all the games end in a resignation. Let me zoom in. From 20,000, from 17,000, 11 are resignations. Which I think is to be expected. If a player feels dominated or has some immediate responsibilities to address, he'll end the game prematurely. Let's see if this is the case with all of the openings. We'll create a similar line plot as before, keeping the x-axis sort, only this time we'll compare the outcome types rather than player color distribution. So we've ended up with another pivot table, the exact same thing that we did before. The only difference is that we're comparing victory statuses instead of the black, white, and draw outcome. We have the draw, we have the mate, out of time, and resignation. So once again, let's visualize this whole thing. As always, I've pre-recorded to save some time. See what we are working with here. Okay, let me zoom in and let's analyze what we have here. From first glance, it seems like these outcomes follow a pattern. Resignations are most frequent, followed by mates, then by out-of-time games, and finally draws, right? However, there are some very interesting insights, I think, to be found. Although the draw line here is very similar to the one that we had here, it is different because here we have the draw rate at 11.1%, and here we can see that it's barely at 10%. So the draw rates differ in both of these visualizations. How can this be true? How can draws differ in these contexts? Before investigating, let me annotate this point right here. So that's what I meant before. Draw rate at this with this opening semi-slab defense is at 10.2% here, and in our previous analysis it was 11%. So the draw rates really are different. Okay, let's investigate why this happened. So to answer this question, let's simply take a look at all the scenarios where our winner column is equal to draw, and our victory status is not equal to draw. Once we have this, maybe we can answer our question. Okay, and what do we have here? So in these scenarios, all of the victory statuses are out of time. So let's see how many of these we actually have. There's 42 instances like this. So there are 42 instances when a draw occurred in a game where a player ran out of time. So that's very interesting. With my limited chess knowledge, I had to ask Google when this would be the case. So the Google answered, in online chess, if your opponent has insufficient mating material when you run out of time, the game is scored as a draw, which is news for me. So yeah, that's how this difference actually is made. So that's actually very interesting. I wasn't expecting to find some new information about chess. Uh, so what other information do we have from this visualization? So for example, that there is a single opening right here. Let me zoom in, which is called the center game. In center game, the mate rate is actually higher than the resignation rate. And that's the only case. And there are three instances of openings having a higher draw rate. So here, here, and here, than out of time rate. So the Semislav, the Zuckertrot, and bird opening. So yes, I think we're done with our analysis. We'll simply write down the final question. And while I copy the question, I would like to thank you guys for watching this video. Once again, if there's any comments or if there's anything else you want me to do, let me know. I'll definitely look into it. I'm really keen into making more Python data analysis videos. And yeah, don't forget to subscribe, leave a like, leave a comment, and see you in the next one. Thanks.